if we want to formally define the idea of torque, we've established that it depends on radius and force. You've got to be applying a force to the object, of course, and the further from the pivot point you apply the force, the more torque you get. So we should expect that torque, usually written as the Greek letter tau, should be proportional to the amount of force you apply. Apply more force, you get more torque. And should be proportional to radius. The further from the pivot point you apply the force, the more torque you get. And it also depends on angle. If you've got just some object, and let's say we mark the pivot point here. Let's say this is a hinge or something where it's rooted in place. And you're applying a force at some location. Let's say you just grab this end of the stick and pull to the left. And then we can also mark the radius vector. And then we have the angle between them, which we usually call theta. So we get the most torque when we have a large radius and a large force being applied. And what angle leads to the most torque? 90 degrees, yeah. So we get lots of torque when theta is 90. We get no torque at all when theta is 0 or 180 degrees. Like if you got this object with a pivot point, if your force is directly away from the pivot point, then your radius vector and your force vector are parallel. Radius vector and force vector in the same direction means the angle is 0. And this means no torque. You can't cause change just by pulling an object outwards from the pivot point. So that would be no torque. And same thing if you're just pushing, if the angle is 180 degrees, your force causes no rotational change, so it doesn't count as torque. So what trigonometric function will work here? What's a trigonometric function that returns a large value when the angle is 90 degrees and 0 if the angle is 0 or 180? Yeah, sine should work here, because if you take a look at the sine graph, the sine graph starts at 0 and goes through cycles like this, hitting its largest value at 90 degrees and returning to 0 at 180 degrees. So the sine function works perfectly here. So we can also say that torque is proportional to sine of the angle between the radius and the force. And those should be the only things it depends on. All that matters is how much force you apply, where you apply it, and in which direction you apply it. So that means we can just multiply these together to get an effective formula for torque. That torque is defined as radius times force times sine theta. So we can use this as a way to calculate how much torque is being applied. You just take the amount of force you're applying, multiply by how far you are from the pivot point when you apply that force, and also multiply by sine of the angle. Any questions on that so far? Also, if we take a look at units of measurement, what is radius measured in? It's just a distance, right? So what do we measure distance in? Yeah, radius as a distance is going to be measured in meters. And what about force?
Newtons.
Yeah, force is measured in newtons. So torque is going to be, oh, and also sine theta is unitless. So the sine of an angle just returns a ratio, which has no units at all. And so sine theta is unitless, which means torque is measured in Newton meters. Technically, you could also abbreviate that as joules. Newtons times meters is joules. But we usually don't write this as joules. Usually we just leave this as Newton meters because torque is not actually a form of energy. It's an action being applied to an object. It's not an energy that the object has. So we usually don't write this as joules because we don't want to get it mixed up with work or energy or heat. So we just leave torque as Newton meters usually. For example, if you have an object that is, let's say, 3 meters long, that's got a pivot at one point, at one end, and you're applying a 10 Newton force to the other end, then you could just multiply those together. Radius times force, and the angle's 90, sine of 90 is 1, so we can ignore that. So we just get 3 times 10 would be 30 Newton meters of torque. And what would that do to the object? You apply a torque to the object, what's going to happen? What does that torque do? It's going to rotate, except what if it's already rotating? I mean, if it's not rotating yet, then this torque is definitely going to make it start rotating. But what happens if it's already rotating? Like, let's say the object is already in the process of rotating clockwise. Yeah, you're going to make it rotate faster. Or if it was already rotating counterclockwise and you apply this torque, what's going to happen?
Slows it down or changes direction.
Yeah, maybe it rotates slower, maybe it changes direction, depending on how much torque you apply and for how long. And this ties into the idea of impulse also, that we saw earlier, that if you apply a force for some amount of time, you cause an impulse, you change the translational momentum. Very similar idea with torque. If you apply a torque for some amount of time, you're causing an angular impulse, which causes a change to the angular momentum or rotational momentum, which is defined in a way that's very similar in some ways to translational momentum, but also different in some ways. It's the same sort of structure, but uses different variables. But this means we're also going to need to consider direction, because as we just saw, if an object is already rotating and you apply a torque to it, whether that torque makes it spin faster or spin slower, or maybe even change the direction it spins, depends entirely on which direction you're applying the torque. That suggests torque is a vector. Torque has a direction, which means we're going to need a way of describing the direction. We've got the magnitude. It's a magnitude of torque. Probably write this as magnitude bars. Magnitude of torque is radius times force times sine of the angle between them. But as for direction, we're going to need a way to define the direction of torque. And we're going to have to be careful about this, because we don't want to just make it the direction of the force. For example, let's say you have a bar that's got a pivot point in the middle. Let's say you grab one end of the bar and push down. Which direction is that, assuming that the bar is not already spinning? If you just grab the right end of the bar and push down, which direction is the bar going to spin? Yeah, it's going to spin clockwise. But what happens if you apply the same force on the other side of the bar? What's that going to do?
Clockwise.
Right, that's going to make it spin counterclockwise. That means that the same force, the same direction of force applied in different locations causes different rotational effects. So we don't want to just say the direction of the torque is the direction of the force, because the torque is more complicated than just the force. The torque has to be a combination of the force and where it's applied, including direction. So we're going to need a way of describing or defining direction of the torque that depends not only on which way the force is pointing, but also where the force is applied. And for this, we're going to use this idea called the right-hand rule. Have you seen anything about a right-hand rule for torque yet?
Yes.
So how would we describe that? If we have, for instance, let's say we are applying this force. So that is, we've got a radius vector from the pivot point to the location of the force. We've got a force vector. And how would you describe the direction of the torque in this case?
I believe it's coming out of the page.
Yeah, it should be pointing outwards from the board. And there are several ways you can find that using a right-hand rule. One way is, the way I usually think of it is if you put your hand at the pivot point and stretch out your fingers straight along the radius, straight towards where the force is located. And note that while pointing my hand this way, I can still swivel it like this. But I want to be able to point my fingers straight towards the location of the force and be able to curl my fingers in the direction of the force. So point your fingers straight along the radius vector from the pivot towards the location the force is applied, and swivel your hand until you're able to curl your fingers in the direction of the force. Then your thumb will be pointing in the direction that we call the torque. So in this case, we'd say the torque is straight out of the board, which we usually draw because it's difficult to draw arrows in 3 dimensions. A vector pointing straight out of the board, we usually just draw it as a circle with a dot in the middle. Outwards or towards the viewer. And the reason for that is it's supposed to look like an arrowhead pointing straight towards you. Like if you have an arrow, like an actual 3D arrow, and you're standing over here, the idea is what you would see is just the tip of the arrow pointing straight towards you. So this is supposed to look like the arrowhead with the tip pointing towards you. Or alternatively, if you're standing over here, what you're going to see is the back of the arrowhead, and you'll see the fletching, the arrows at the back. So this represents a vector pointing inwards, into the page, into the board, into the screen, away from the viewer. Inward or away from the viewer. So those are the 2 ways we draw a vector pointing outwards or towards the viewer and a vector pointing inwards or away from the viewer. Just the convention, the notation we use for those directions. Because there are many situations where we need to be able to draw vectors in 3 dimensions. So we've got left, right, up, down, and also outwards and inwards. But in this case, it looks like the torque is outwards from the right-hand rule. You could also think of that as asking yourself which direction, if this torque were the only thing acting on the object, which direction would it make it spin? Spinning this way. So if you curl the fingers of your right hand in the direction it's going to make it spin, if that was the only torque, then that also has your thumb pointing outwards. There's also probably some way you could do it with 3 fingers. If you have like, maybe point your thumb in the direction of the radius, point your first finger in the direction of the force, and your middle finger will tell you the direction of the torque. So that would also work if you prefer to do it that way. But there's a lot of different variations on the right-hand rule. They're all just ways of deciding a direction. And ultimately what any right-hand rule is talking about is you want a 3rd direction. We've already got 2 directions, radius and force. There's a lot of situations, more generally known as cross products. A cross product is a situation where you have vectors in 2 directions and you're creating a 3rd vector in a direction perpendicular to both of those. So if we have radius this way and force this way, and we need to create a 3rd vector that's perpendicular to both of those, what are the only possible directions that are perpendicular to both of these?
Towards you, right?
Yeah, in this case, either towards the viewer or alternatively away from the viewer. So if all we care about is the perpendicularity, the idea that torque has to be perpendicular to the force and perpendicular to the radius, there's 2 possibilities here, outwards or inwards. The right-hand rule, the real purpose of any right-hand rule, and we're going to see more in 7C also, is to choose one of those 2 directions. If you've got 2 vectors and you need a 3rd vector that's perpendicular to both of them, there's always 2 options. In this case, outwards or inwards. Or if it was like this, your options would be to the left and to the right. The purpose of a right-hand rule is to just choose one of those 2 directions. And it's kind of arbitrary. We could define all of physics using a left-hand rule instead. It would still work, you just have opposite results for some things. But it would still work just fine. But for consistency, we need to be all using the same version. So we just arbitrarily choose the right-hand rule. So radius, force, torque is going to be pointing outwards in this case. Does that mean that any piece of this is moving outwards? No, it's going to be spinning. If anything, it's going to be spinning like this. So nothing is moving outwards. The important thing about outwards in this case is that it's the axis of rotation. This object is spinning around an outwards axis. So the direction of torque is really talking about an axis that the object could be rotating around. And the same is going to be true when we establish a direction for angular velocity, angular acceleration, angular momentum, and all of this rotational stuff. Anything defined as a vector, the direction of that vector is just talking about the axis the object is rotating around. Any questions on that so far? So I think that gives us all the important information about torque as a vector. We've got its magnitude defined by radius times force times sine of the angle between them. We've got its direction defined by the right-hand rule. And we know what it does is it causes a change to the rotation. Maybe the object's not rotating and it's going to start rotating, or maybe it's already rotating and the torque makes it spin faster or spin slower, or maybe even spin in a different direction. For instance, if I've got an object that's spinning like this and I tilt the axis it's rotating around, that counts as changing its rotational momentum. Spinning, but changing the axis it's rotating around. Because the axis of rotation is what direction is all about here. Any questions on torque so far? And a couple other bits of geometry here that sometimes become important. There are other ways you can calculate torque involving radius and force that don't always involve sine theta, at least not directly. For example, let's say we have the ground and we have a sort of a bridge type thing, some sort of structure like this. And let's assume that this structure is very lightweight. The structure itself has very small mass compared to, let's say we put something heavy on top of it. Let's say we put a car on this. Maybe we have a car dealership and we're putting a fancy car on display to show off how awesome it is. So we've got this car on display here on top of this lightweight structure. And of course, we'll want to put in some sort of supports to hold it up. Because without any supports holding it up, this is just going to collapse. And specifically, if this did collapse, if this started to rotationally collapse, what point do you think it would be rotating around? Where should we call the pivot point here? If this whole structure starts to rotate.
Where it's touching the ground?
Yeah, presumably that point where it's touching the ground would be the pivot point. If we assume the structure itself is fairly rigid, so it's not going to break or anything, if this collapses, it's going to collapse by just tilting downwards like that. So let's treat the point where it connects to the ground as the pivot point. Because if it did start to rotate, that's the point it would all be rotating around. So we've got a pivot point. And which direction or where is the force applied here? If we're talking about the structure itself, what force is acting on the structure? We're going to get a downwards force from what object? Or at what location? Yeah, the car itself, because the car is heavy. Gravity's pulling the car down. If we want to make sure the car doesn't fall, the structure itself needs to be holding the car up. But of course, that means by Newton's third law, if the structure is holding the car up, then the car is pushing the structure down. So the structure is experiencing a downward force from the car itself. That's the force, and technically that is a normal force. It's the force of contact between the surface of the tires of the car and the surface of the floor of the structure. So we've got a normal force on the structure from the car. So that's the force involved. And how would we draw out a radius vector here if we wanted to calculate torque? The force from gravity, I mean, ultimately the reason this exists is because of gravity. But the reason why we don't call it a force of gravity is because this is not the force of gravity on the structure itself. What we care about is the object we care about here is the structure. And gravity is technically influencing both of them. If we take a look at the structure, and the car, the structure is experiencing a force of gravity because the structure has mass and the structure is located on a planet or near a planet. But where would you expect the force of gravity on the structure to be located? Yeah, gravity is pulling on the structure everywhere, but we can average out that everywhere force to what single location? Right, the center of mass, which is, let's say, right about here. Because it's going to be influenced by both this bar and this bar. So gravity is a small force pulling on every single atom of this structure. But we can treat it as just one big force, lump all those forces together, and treat that force as located at one single point that we call the center of mass of the object. So here we've got this downward force of gravity from the Earth on the structure. So the force of gravity is a force from the Earth acting on the structure. But that's not the force we're talking about here. This force is because if we take a look at the car is also experiencing a force of gravity. The car is experiencing a downwards force of gravity from the Earth. Force of gravity on the car from the Earth, which is presumably much larger because we were assuming that the structure is very lightweight. We're assuming we've got a very lightweight structure and let's say a very heavy car. So we've got a very strong force of gravity on the car from the Earth. But the car is not falling because what other force is holding it up? What's preventing the car from falling here? Yeah, we've got a normal force from the structure itself. So the car is also experiencing an upwards normal force on the car from the structure. And these have to be equal in magnitude because we know they add up to 0. Same magnitude. But if the car is experiencing an upwards normal force from the structure, then the structure also has to be experiencing what? An upwards force? It's exerting an upwards force on the car though. So what does that tell you? If the structure is pushing up on the car, then what's the car doing? Right, the car is exerting a downward force on the structure. These are the equal and opposite forces that Newton's third law is talking about. That the structure is pushing the car up. So that means the car is also pushing the structure down. So we're going to have, at the location of the car, we've got a strong downward force, exactly as strong as this one, because it's really the same force, just looked at it from two different perspectives. This is the normal force on the structure from the car. So this is why we don't call this force of gravity. It's related to the force of gravity, but it is not actually a gravitational force. This force is the force of the car's tires pushing down on the structure itself. whereas force of gravity is the force of the Earth pulling on the structure downwards. And in this case, that's going to be fairly weak because we're assuming the structure has a small amount of mass. The main force here that we need to consider is the normal force of the car pushing downwards on the structure. So that's the normal force we're talking about here, the car pushing down on the structure. And it is the same amount of force as the weight of the car, the force of gravity on the car. But it's not a force of gravity on the structure. It's the force of the car on the structure as a result of gravity. But it's an indirect result of gravity. In fact, the normal force of the structure on the structure from the car doesn't even have to be the same as the force of gravity on the car. It just happens to be the same because we know the car is not accelerating, and therefore these forces have to balance each other out. If there was acceleration, though, this would not be the same as the weight of the car. Any other questions on that so far? So the structure itself is experiencing a downwards force caused by the car. It's also experiencing a downwards force from gravity in its center of mass, but I think we can assume that that's small enough we can ignore it. We can focus on just the strong force from the car itself. And how would we draw out the radius vector here? If we want to calculate torque, we're going to need a radius vector. So that would be a vector from where to where? Yeah, from the pivot point to the location of the force. So this would be our radius vector here. So we've got a radius vector, we've got a force vector, and there are actually several ways we can calculate torque here. One of them is using the usual r times f times sine theta. So we can say torque, and I'm just talking about magnitude here. The direction is going to be from the right-hand rule as usual. Radius vector is literally just the distance from the pivot point to the location where the force is applied. So for instance, maybe this location where the car is pushing on the structure, maybe that happens to be 3 meters away from the pivot point. So the radius would be 3 meters. And it counts as a vector because direction matters. 3 meters to the right and up versus 3 meters straight up versus 3 meters straight to the left. Those are all different locations. So direction does matter here. Radius does count as a vector. In the formula for torque, though, we're treating radius and force as magnitudes. So just the amount of distance times the amount of force times the sine of the angle between those vectors. But the fact that they're vectors is important for the purpose of this angle. So direction does matter in that context. Any questions on that so far? So to find the torque, you would just multiply this distance times this amount of force times the sine of this angle. But there's some other geometric tricks we can do here that sometimes makes the calculation easier. For example, if we think about what sine of theta means in a right triangle context, if we have a right triangle, let's say we just call these side lengths A, B, C. What would sine of theta represent in this right triangle? Or in any right triangle, what does sine theta represent? Yeah, in this case, that's going to be A over C, the opposite side divided by the hypotenuse. So sine of theta, sine of an angle between vectors, is a ratio of sides of this triangle. And this right triangle idea suggests that it might be useful to split up the vectors into components. But it's not necessarily going to be x and y components as usual. The components we're going to be splitting these up into are, we're going to be splitting one of the vectors into a component parallel and a component perpendicular to the other vector. For example, if we have this radius vector, and we have this force vector, let's say we split up the force vector. Instead of splitting the force into the usual x and y components, which aren't going to be as useful here, we can split up the force into a component perpendicular to the radius and a component parallel to the radius. So to do that, it's almost like we're establishing a new set of coordinate axes. Instead of the usual axes of x and y, we're going to have a tilted axis. So we're going to have one axis that's parallel to the radius and one axis that's perpendicular to the radius. So instead of the usual x and y axes, we're going to have a parallel axis and a perpendicular axis. And sometimes these axes are called x and y anyway. I usually call them the parallel axis and the perpendicular axis in order to avoid confusion with the usual horizontal and vertical x and y axes. But we're going to be splitting the force into a parallel component and a perpendicular component. So for the parallel component, we're just kind of have a component in the direction of the force of the radius itself. And then we're also going to want a component perpendicular to the radius. So it might help to just take a pencil or another straight object and tilt it around until you can get a perpendicular. And then tidy up the excess bits. So here we have a triangle with the force vector itself as the hypotenuse. We've got a parallel piece and we've got a perpendicular piece. So we could call these F perpendicular and F parallel. The amount of force that's parallel to the radius and the amount of force that's perpendicular to the radius. So we could split this force up into those components, and this angle theta will be one of the angles in that right triangle. And this is almost exactly like splitting it up into XY components. The only difference is we're using this tilted axis. So we've got a parallel component and we've got a perpendicular component. The parallel component is also sometimes called the radial component. Radial in the sense that it's in the direction of the radius, or sometimes exactly opposite to the direction of the radius, as is the case here, but parallel to the radius. And then the perpendicular component is also sometimes called the tangential component. Tangential as in tangent line to a circle. Like if you were to start actually swiveling this, it would form a circular path with the r vector as the radius of that circle. The tangential direction is parallel to a tangent line to the circle. So the radial or parallel direction is parallel to the radius. The tangential or perpendicular direction is perpendicular to the radius, which would be parallel to a tangent line to that circle. But the idea is we're splitting up the force into components using axes based not on the usual x and y, but based on the radius itself. And how would you actually calculate F parallel versus F perpendicular here? Assuming you know the force and the angle. How would you split that vector into those components? How do you usually split a vector into components if you know the magnitude and the angle? Right, you use sine and cosine. So to find that specifically, and sine is going to be the important one here, because sine is what we actually care about for finding torque. If we calculated sine of this angle, which ratio would sine of this angle specifically equal? Yeah, sine is going to be the perpendicular component divided by the whole force. F perpendicular or F perp, sometimes abbreviated as, divided by the whole force. Which means if we multiply both sides by force, we get F perp equals F sine theta. And note that F sine theta is exactly what shows up in the definition of torque in the first place. So this F sine theta could be interpreted as, if you could just bundle all that together, F sine theta is the perpendicular component. So instead of taking the entire radius times the entire force times the sine of the angle, one thing we can do here is drawing a perpendicular component and we can say, ignore the force, just multiply the complete radius times just the perpendicular component of the force. And sometimes the perpendicular component of the force is easier to get. In this particular case, I don't think it would be, because you'd have to, presumably the force is just the weight of the car. So in this case, I would presume the force is already known, but finding F perpendicular in this case would require knowing the angle. And if you already know the angle, you may as well just multiply r times F times sine theta. But there are some cases where the perpendicular component of the force is easier to find. For instance, if the perpendicular component of the force happens to be one of the components you're already splitting the force into, maybe F perpendicular happens to be just the y component anyway. If you're already going to be finding the y component, then you don't even need to worry about the angle. You can just multiply the complete radius times just the perpendicular component of the force, and that is the amount of torque. So this is an alternate way of calculating torque that is sometimes very useful. Instead of writing r times F times sine theta, we can write it as the complete radius r times just the perpendicular component of the force. If you don't know the angle, well, if you already know the perpendicular component of the force, then you can just multiply the perpendicular component of the force times the complete radius. And that might be, maybe for instance, the force is already perpendicular to the radius. If you're dealing with a situation where the force is perpendicular to the radius, then the perpendicular component of the force is just the whole force. So if the angle is already 90 degrees, you can just multiply radius times force. Or if there's some reason why you're already going to be splitting the force into components, and one of those components is perpendicular to the radius, then you can just multiply the complete radius times the component of the force that's perpendicular to the radius. And that'll tell you the torque. So this is sometimes useful if the force is already perpendicular to the radius, or if you're going to be splitting the force into components anyway. And that's often the case. There are, in a lot of situations, you already want to split all the forces into x and y components, or into some sort of components. So if you can set things up such that the components you're splitting the forces into are already parallel and perpendicular to the radius, then this formula can sometimes be much more convenient. Or alternatively, there's a third option. Instead of splitting the force into components based on an axis from the radius, we could split the radius into components using an axis based on the force. So drawing out this exact same situation again, radius vector and force vector. In this case, instead of drawing out a vector, or instead of drawing out axes parallel and perpendicular to the radius and splitting up the force, let's try the opposite approach. We'll draw out axes parallel to the force and perpendicular to the force. So force is straight down, so the parallel axis is going to be vertical. Perpendicular to that would be horizontal. So in this case, it does work out to just the usual x and y axes. But more generally, we want to take an axis parallel to whatever direction the force is in, and another axis perpendicular to that. And then we're going to split up the radius into components based on the force as axes. So we're going to take the radius, split it into a component parallel to the force, and a component perpendicular to that. So parallel component, and for the perpendicular component, what I would usually do is just take your pencil or whatever straight object you have at hand, hold it parallel to the force vector, rotate 90 degrees, and then just start sliding this up and down until you can get a straight line that's perpendicular to the force and hits the other end of the radius vector. So this is the vector triangle we're considering here, and then tidy up any excess bits. But we are now splitting the radius vector into a perpendicular component and a parallel component, r perpendicular and r parallel. And we're still going to be doing this based on the angle, which again was the angle between the two vectors, angle between the radius vector and the force vector. And in this context, in this triangle, what would sine theta represent? What would that ratio look like in this triangle? Yeah, sine theta is going to be opposite over adjacent, or sorry, opposite over hypotenuse. That's r perpendicular over r perp divided by r itself. And again, we can multiply both sides by r and say the perpendicular component is r times sine theta.
Oh, wait, sorry, Casey, question. Why would we draw it differently? Like, why would we draw it this way versus the first way you drew it?
It's just two different ways of focusing on how we're going to split up the vectors. We could keep the radius, the previous way was we kept the radius exactly as is, but we split up the force vector into components using axes based on the radius vector. Now we're trying the reverse approach. We're keeping the force exactly as it is, but we're splitting up the radius into components using axes based on the force vector. So just two different ways of setting up a coordinate system based on the other vector.
Thank you.
And the reason this is useful here is this gives us another substitution we can make. Instead of replacing f sine theta with f perpendicular, we can make the other substitution. We've got an r sine theta, and order doesn't matter for multiplication. We can shuffle these around. R sine theta can be replaced with r perpendicular. So this gives us a third formula for torque. R perpendicular times F. So this is two equivalent but different looking ways to do this. You can take the complete radius times just the perpendicular component of the force, or you can take the complete force times just the perpendicular component of the radius. And in this context, this formula is actually going to be significantly easier to apply. Because if you actually draw out the perpendicular component of the radius, in this context is physically much easier to measure. In this context, because the force is vertical, since it's a force caused ultimately by gravity, since the force is vertical, r perpendicular is just the horizontal component of the radius. You could almost think of that as like the shadow cast by the radius on the ground. And this is going to be significantly easier to measure. If you were doing r times f times sine theta, you'd have to know the weight of the car, which is presumably known. You'd have to get out some sort of measuring device that can measure this diagonal distance, which might be very high up and inconvenient to access. And you'd have to have some way of measuring this angle. But if you're using r perpendicular, that's just a distance flat along the ground. You could just pace off this distance with a measuring tape or a ruler or whatever. Distances along the ground tend to be very easy to measure. So one way to calculate the torque here from a practical standpoint is to just measure the distance along the ground from the pivot point out to the location on the ground directly under the car, multiply that distance times the weight of the car, and you're done. That is the torque that the car exerts on the structure. And then, of course, if you want to hold this in place, you would need to have some other supports that cause an equal and opposite amount of torque. Maybe some support pillars here, or maybe some cables hanging it from something higher up, in order to make sure that it does not rotationally accelerate, make sure it stays still. You need to apply an equal and opposite torque, or maybe several torques, just so long as all the torques add up to 0. That's really the key of making sure something is stable. You want all the forces to add up to 0, so there's no translational acceleration, and you want all the torques to add up to 0, so there's no rotational acceleration. Correct. The torque is not in the same direction as the force. In this case, the force is downwards, but which direction would the torque be in this case? If we've got radius this way and force this way, so radius and force, First of all, the torque has to be perpendicular to both of these. What are the only possible directions that are perpendicular to both of these vectors?
In and out.
Yeah, outwards and inwards. And in order to decide one of those, we would use the right-hand rule. So my usual way of doing that, put your hand at the pivot point, stretch your hand straight along the radius vector, and curl your fingers in the direction of the force. Might be easier to see if I'm over here. Hand at the pivot, right hand at the pivot point, stretch fingers straight along the radius vector, swivel your hand until you're able to curl your fingers in the direction the force itself is pointing. And your thumb, in this case inwards, tells you the direction of the torque. So the torque in this case is inwards. Torque is into the board, away from the viewer. So that's the direction of the torque, as ultimately meaning that it's going to cause some sort of clockwise effect. And the magnitude is going to be this horizontal distance times this force. Perpendicular component of radius times the entire force. And I want to emphasize all three of these formulas will give you the exact same result. They're all equivalent formulas. They're ultimately just different ways of writing out the geometry. But in certain cases, one or the other of these might be much more practical to actually use. Like in this case, measuring this horizontal distance is going to be much easier than measuring the diagonal distance and measuring the angle. So you want to pick whichever one of these formulas involves information you already have or information that would be easy to find. And then you can just ignore the other formulas. But it's useful to know all three of them or be able to derive all three of them from one or two of them from the other, because each one can be useful in different circumstances. Any other questions on that? All right, then we will look into more examples and angular momentum next time. Feel free to email me if you have any other questions, and I will see you later.
Thank you.
You're welcome.